Yeah, good morning, everyone. So we are today here with our talk. Have you ever wondered how a cloud platform works? And for this, we structured the talk into Cloud Foundry. What is it and how does it look like? The cloud controller and its database, and in the end, some operational insights and PostgreSQL tuning, which we performed. So, Cloud Foundry, what is it and how does it look like? But first, before I tell you what Cloud Foundry actually is, we need some, or describe the problem statement of a cloud platform, especially a platform as a service, because as developer, you mainly want to focus on your code, on your application code, and don't want to bother with infrastructure things. For example, provisioning virtual machines, setting up the network, then continuing with the build and packaging of the application where you have to upload to some artifact repository or building container images. And then going further, configuration management, how is the application configured in the runtime. Also, when your application runs productively, you also want that you get some insights like logs and metrics. You want to see when something goes wrong and act on it. And if you perform updates, you want also the capability to just roll back. But doing this manually, this is a really hard topic. So as a developer, how would it be if you just have a platform where you hand it over just the code, let the platform do its thing, but you don't care how the platform does it, but it does it really reliable. This would be really great if we could just have this. And this poem here, or a haiku, this briefly describes what Cloud Foundry in the end basically does for developers. And Cloud Foundry is an open source platform as a service. And it does not belong to one company. It is overseen by its own Cloud Foundry Foundation. And which is part of the Linux Foundation. So SAP just cannot decide what will happen with Cloud Foundry. It is like a combined decision of the foundation. So Cloud Foundry is a platform to deploy and scale your applications. And it is designed for cloud-native applications built in a 12-factor style, so stateless and environment-based config and so on. You can look this up, these 12 factors. And Cloud Foundry works with a variety of languages, so you don't have, for example, a Java server, where you just only can run Java applications. You can do nearly anything with it. And you don't need to, you just deploy your apps from the source code, and you don't have to care about container images. It's just your code. You put it to the platform, and the platform runs it. So why you should care as developer for Cloud Foundry? You reduce the infrastructure complexity, so you don't have to care about provisioning anything like virtual machines, networks, or containers. And having this taken away from you, you can really focus on your application and deliver faster what you're currently building. And furthermore, when you go then into production, and want to see what's happening, what are the problems of my application, you also have directly built-in observability, and not only for logs, also for metrics. And in the end, you could nearly bring anything to the platform. You can run Java applications, Python, Go, anything, but not ABAP. This is another topic. Probably you have never heard of Cloud Foundry, which is a bit sad because we are one of the top 10 Linux Foundation projects. So maybe years ago, Cloud Foundry was a bit more popular in the community, but it did not disappear. It's really alive and really active. So, but it takes a while until we can keep up with the Linux kernel. So now to the core concepts of Cloud Foundry. So what you as a developer have to deal with when you build applications with Cloud Foundry. First of all, you have the application itself, which you manage over the command line most of the times. And the application is just the representation of your source code, which is then put into the platform and then also scheduled to run. Then you have also build packs and stacks. So your code is taken, and with build packs, they are actually transformed into a runnable container. And the stack is the base image for this container, so that every dependency is then packaged together and being a runnable artifact. But applications on its own does not do the job. So you also have services which are attached to Cloud Foundry. And services are, for example, Postgres databases or autoscaler or whatever you can imagine, something which supports your applications. And they are not part of Cloud Foundry itself, they are just attached with a standard definition to it. So Cloud Foundry just depatches it then to the service implementations. And to separate your resources, there are orgs and spaces which can separate the different apps to different teams or departments. And just one word to the services. You can also decide for services which service plan you use. So, for example, when you provision a Postgres database, there's not only one size. Maybe you need for one microservice a small database, like with 2 gigs of memory and a small processor, and for another microservice, which is a bit more monolithic, you need a really big database with 512 gigs of RAM. So you can also do this with service plans. And now it gets a bit more hands-on. So how does it in the end work? When you bring your application to Cloud Foundry, you have your source code and an optional small YAML definition, the manifest, where you can define, for example, the route of the application and which build pack you want to use. And then you execute just a cf push command on your terminal, and then you communicate with the Cloud Foundry API. There you upload your source code, and this is the cloud controller, which Philipp will speak about in a minute. And then the cloud controller triggers the app staging, which is the first phase, which is kind of a build where the image is produced. This image, the app droplet, is then uploaded to a blob store, and after that the Cloud Foundry API knows, okay, the build is ready, we can now take the application and start it and serve it to the users. So when the app starts, a health check is performed, and also all the services are then connected to this application, and then you have your running application. So this is like the process, what will happen when you do a CF push. But let's see it in action. So I created a small Python application for this conference, and I executed a CF push. So the source code is uploaded, and now it starts with the staging. It automatically detects the dependencies of the application, like the requirements.txt file in the for Python app, downloads all the dependencies, welds them together with the stack. And now, the container image is uploaded, and it starts scheduling the application, and it's running. So, and automatically there is also a route attached, and here you see I can also reach it with curl, and the app greets you on every location for a conference you can imagine. So, and that's it. It was nearly a minute from I have my source code to a running application. So, but how does it look like? What are the components for this for Cloud Foundry? So each request enters Cloud Foundry over a routing component, which is then either forwarded to the applications or to the control plane, like where also the cloud controller resides. And there we have the most important database, which is attached to the cloud controller. So, and the cloud controller then interacts with the Diego subsystem, which you can imagine like a leader-worker pattern. You have the Diego control plane with the scheduler, which actually takes care to distribute the workloads in the Diego cells, which are on the right side of this diagram. And so we have some databases which are serving Cloud Foundry and enabling you as developers to deploy your applications really fast. So now, Philipp.
Okay, so does it work? No, it's working fine. So after Max gave you the overall picture about Cloud Foundry and its components, I will talk a little bit more in detail about one of the components, the cloud controller, and especially its database. In fact, if you have a Cloud Foundry foundation or landscape, we use both terms identically. So we mean an installation of Cloud Foundry. This comes with 6 Postgres databases. And the database from the cloud controller, the CDB, is the biggest one. So just a short repetition, what is the cloud controller? It's on the one hand the API gateway, so all clients, be it users or automation pipelines, talk to the CF API. So all requests, be it the CF push that Max just demonstrated, or the creation of a service, querying for information of organizations and so on, are handled by the cloud controller. So all this metadata that make up this cloud platform are stored in the CCDB. And when this database becomes slow, or when the interaction between the cloud controller and the database becomes slow, then you feel it. And for example, the CF push suffers, and all other interactions also suffer. Some words about the stack, the technology stack of the cloud controller. So it's implemented in Ruby. It's a Ruby on Rails application, but it does not use the default persistence framework, which would be active records for Rails applications. It uses a different library called SQL. SQL, on the one hand, is an ORM mapper, so you can define models, you can define relations between these models, but it also provides you with a quite nice SQL DSL, so you can build SQL queries with this, which are database agnostic. So Cloud Foundry itself supports Postgres and MySQL, so when you take the open source Cloud Foundry installation, you can decide which database you want to use. But we at SAP, we use Postgres. And yeah, originally Cloud Foundry was designed for, let's say, smaller deployments. In the meantime, SAP runs the largest Cloud Foundry foundations in the world. And with this, we revealed some inefficiencies. And in the area of the cloud controller, this was mainly due to how it interacts with the database. And as these performance issues then became scaling issues of the whole landscape, scaling was limited because things get slower. We got more and more involved into the development of the cloud controller and improved how the interaction with the database is done. So here are some learnings. Two small sample Ruby code snippets. I mean, the good thing of an ORM is you don't have to think about SQL, right? You just write your code and magic is happening behind the scenes. So if you want to check if a table is empty, if there are entities of a specific data set, you could think, okay, I just check if the count of this data set is 0, which emits a select count, which is not the cheapest option. I mean, it calculates the exact count, but for this query, it's just not necessary, right? You want to see if there are entries at all. So by changing this to a different method, here it's the empty method, the SQL behind the scene changes to a much more efficient one, where you just check if there is one entry at all. And we found similar patterns throughout the code. So for example, I'm interested in one specific field. So in database terms, it's a column of all my entities in a database table. So the normal Ruby pattern is, I select all the objects, and then I just access this one field for every object, which in the end leads to a select star on the table, and it builds for every entry, it builds an object, this ORM, just to throw away most of the information. By realizing what actually should be achieved here, you can switch to more efficient ways of doing this. So SQL provides, for example, the select map method, where you give the field and it does a select only for this column and also does not create all the objects. It just returns a simple list of values. So with an ORM, you have all these relations, and it's nice. You can follow them. For example, if you have a process at hand and you want to know the GUID of the application it belongs to, you just do process.app, then you navigate to the application, then .GUID, you access the GUID field. What happens behind the scene? By following this relation, it just issues another select, so it selects from the applications where the GUID is the GUID that is stored there. The GUID of the application seems to be the foreign key here. So we want to know the foreign key, then we just simply can replace this by accessing the foreign key directly on the object that we already have at hand. So by simply knowing what's happening behind the scenes, with small changes, you can optimize the queries. You can omit queries that are not necessary at all, or you can make queries far more efficient. So our key takeaway for this topic is when you work with an ORM, simple code doesn't mean simple query. You really have to know what's happening behind the scenes. And we do this by logging and reviewing the SQL statements during development. So whenever we touch an endpoint and we change stuff, we don't only rely on, it's working functionally, but we also review the SQL that is issued to see if this is a performant way of doing this, or if there are things that could be improved. So this led us then to the next topic. We want to systematically analyze the performance. So that's why we contributed a suite of API performance tests that run in a pipeline for every release. It runs here for Postgres and MySQL, so we can see the differences and we can see trends over time. And the following graphs give you an idea how the results look like. So there are some endpoints where we could really improve the performance drastically. So for example, for the service plans endpoint, it was just really, really slow, 30 seconds for an answer. It's now factor 10 improved. But of course, this is not the factor you always get. There are other endpoints where we could improve the performance over time, so with incremental optimizations. And especially these performance tests are useful to detect regressions that you can see on the bottom diagram. So for the roads endpoint, with some change, we introduced a regression, and then we detected this and could improve again. But these synthetic performance tests are only one part of measurement, I would say. More importantly is observing in production, and for this we collect for all the interactions between the cloud controller and the database, we collect metrics, and very helpful for us is a visualization in the form of a heat map, where we have the runtime on the one axis, and on the other one it's the location in the source code, and then the color indicates how often this is called. So this helped us really to see where in the production landscapes are the bottlenecks, which queries are often executed, which ones are slow, and where to focus, and also where to add new performance tests. One big, besides using this ORM, where you don't know what's happening, another difficult issue are dynamic queries. So for example, the service plans query, which was the one that you saw before, which we could improve drastically in the end. It's a dynamic query because the cloud controller endpoint has many parameters. So clients can filter by all sorts of things. And the service plans depend very much on the foundation that we are running. So how many services are configured in this landscape, how many offerings are there, what different kind of plans are there. And when you access this endpoint, it checks which services are visible for a specific user. So there is a permission check. So this is all rendered into one huge SQL statement, which becomes very slow depending on the data size that you have. And it's also very unpredictable because in many foundations things are fast, but then there are bigger foundations where then things get worse, or there are special users that have many permissions, and then it becomes worse as well. In the end, it was also understanding what's happening behind the scenes. So what is the ORM doing, and then bringing it into the direction of making better queries by specifying the queries with this SQL DSL that's available in SQL. So there were initially just all the tables that could potentially be involved were joined. Now we removed all tables that are not relevant because there were no filter parameters for them. There were very huge in lists which could be replaced with subqueries, so could be shifted to the database, the heavy working, and the database could better optimize than these subqueries. We replaced the distinct that was checking the whole result set with a distinct on, just checking that the ID is different. But the main improvement was to split up very, very complex OR conditions. So all the user permissions, does the user have permissions in a specific org, in a specific space, and so on. They were all modeled in these complex OR conditions, and we were able to split this into several selects that are union together in the end, and this became then, let's say, more planner friendly, so the planner could optimize all the subselects better, and this came to, in the end, to a more predictable performance across all the foundations that we have. So our lessons learned here is to make the planner's life easier. So of course you can add indexes, you can try to influence the planner when you see suddenly there's a plan switch and you want to understand it, and then you try to influence it. But if such things happen, then that's quite often a good indication that maybe your query is too complex and you could think of changing the query and simplify it. Then another topic, so the last topic I'm talking about is schema migrations. It's not a static platform, right? It's evolving. There are new features added, and this means that also the database has to change, and of course we don't want to have any downtimes. There are simple migrations like adding a column or introducing a new table, adjusting some constraints and so on. But there are also larger migrations that you will see on the next slide. And for us, all these migrations are part of the software release cycle. So they are in the code of the cloud controller. So every new version of the cloud controller might contain a migration, which is then automatically executed when the new version is deployed. So the larger migration was a big int migration for primary keys. So if you heard the talk yesterday about things that you shouldn't do in a Postgres database, so when 10 years ago the initial schema was created for the cloud controller database, someone thought int for primary keys is enough. So there was especially one table. It's called events, like the name is saying. It's transient data that is deleted after a retention period of, for example, 14 days, but still the primary key counter is increasing again and again. So on one very large foundation, we would have hit the 2 billion row int limit end of this year. So we had to do something about this. In theory, for this table, we could simply have reused the ID, so we could have done a rollover because the old data is deleted. But this sounded like a bad idea, and we wanted to do this consistent and future-proof that it can also be applied to other tables. So we implemented the big int migration. And it's a 3-step migration. So you prepare some things, introduce a new column, create triggers that automatically fill in the same value as in the old ID column. Afterwards, you have to backfill the data for the existing columns, and then in the end, if everything is consistent, you can switch the constraint and drop the old column. The good thing here for this events table, due to the retention policy, there was no backfill needed. We simply deployed the first step, the preparation, and then we waited 4 weeks, and this ensured that there was no data with missing big int value, and then we could apply the third step. So this has been implemented in a reusable fashion that we could then also easily do the same for other large tables, and they are now already migrated to big int. But of course, it's a journey, and we want to do this for all the tables. And yeah, the next challenge then is to migrate tables with foreign key relations, where you also have to touch the foreign key. So what we learned about this schema migration things is that, yeah, the one thing is it has to be backwards compatible, because during the release we update the database first, and there are many clients talking to the database, so the Cloud Controller runs with several instances, and there are also worker processes that also access the database. And so you always have to ensure that the schema is compatible with the old version of the code. We, in the meantime, after learning this the hard way, introduced automatic tests that really run the full unit test suite against the old version of the code. Then you have to plan carefully for your migrations. It's better to have more smaller migrations than big ones. And of course, you have to test it on realistic data. So we take, whenever we have a migration, we take snapshots of our 2 largest foundations, and then run the migrations against these databases created from these snapshots. The good thing, it's the same data, so you get an idea about the timing, how long does the migration take, but of course it's without the load, so it's not 100% perfect. But for this, we also have the staged rollout of the migrations. As I said, it's part of the software release, the migration. So yeah, we ideally see issues in our QA systems before they hit production. Okay, now back to Max.
So let's talk a bit about the operational insights and the PostgreSQL tuning. First, how do you get your Postgres or your database for Cloud Foundry? Here a snapshot from the deployment guide. So you can run with MySQL or with Postgres. So for this conference, we removed the noise and only focus on Postgres. And you could use a Postgres release. Cloud Foundry is installed with a release engineering tool called Bosch, also of the Cloud Foundry ecosystem, which is just like a blueprint which installs then the software on virtual machines and configure the virtual machines into these big deployments. And but when you not want to use a Bosch release like the Postgres release, you could also just connect any other Postgres database from version 13 to 15 and get running. So, but the Postgres release has some downsides. It is by design not high available, so this is not a good idea for production scenarios, because when this databases stop because of zone outages or something in the data centers, we are just offline. So we use hyperscaler services to provision our databases, And we run on multiple ones, on all big ones, for example, AWS RDS, Azure Flexible Server, GCP Cloud SQL, and Alibaba Cloud Apsara, which is a bit exotic. So when you provision a hyperscaler Postgres database, you might assume, oh yeah, okay, they have Postgres, they have infrastructure as anyone else. They have more or less the same servers on the x86 platform. Everything is from Intel. They also have, every one of them have their kind of comparable network storage which they attach to the virtual machines. But actually, when you just look at some of these parameters, it's completely different. So, for example, with the random page cost, AWS and GCP assume they have slow disk drives, and Alibaba is like light speed for random page access. Also with the max connections, because in the deployments there are a lot of worker processes for the cloud controller, and therefore each worker has its own connection pool, and so the max connections are also one of our bottleneck resources. So this was also a challenge for GCP Cloud SQL. And there the challenge is, okay, you see these numbers, but you don't know why they tuned the database like this. So also we have to do some research to figure out what we can configure there without performance impacts, and same also for the shared buffers. So yeah, you might expect you get everywhere the same, but you don't. It's completely different on each for each vendor. So, and now when you are running with production landscapes and customers, you also have to do migrations from time to time. So we performed some time ago a migration from Postgres 11 to Postgres 15. Yeah, this went well on all infrastructures, like every infrastructure provider performed well. So we have our different stages. Yeah, dev systems worked, also test, QA, also production landscapes were migrated, also worked. Yeah, we also had some weeks of experience running these databases on Postgres 15, but one landscape was left. And this turned out to be really problematic, because after some time the cf push command failed. So this means users could not upload apps or perform lifecycle events to the applications. So you might assume we did this. Actually not, it was only one database which were problematic. And for us it was also a real rare case we had seen there. And we could trace it back to this one parameter, the max parallel workers per gather equals 2, which was a default setting. It was introduced in Postgres 10, and for us it had no effect on Postgres 11, so actually no problems, we could leave it like this. These workers are shared across all these different Postgres processes, for example, for the wall writer, query planner, query execution. And what happened, in this case, the query planner assumed it could always take 2 workers for the query planner and for the execution. And so the plan is also optimized for parallel execution. And unfortunately, there's no replanning if no workers are available. So the query planner just hands out these parallel workers, like that there is no bottleneck, but actually there was a huge one. So this resulted, these parallelized query plans resulted in immense CPU load, and also it blocked incoming queries. Like the database was completely unusable. This is like this, yeah, you don't want to experience this because it's really bad. Yeah, the quick fix for this, for us, was just to disable this feature. And you know how it is with quick fixes. Yeah, and also quite interesting, some words from the documentation. Note that the requested number of workers may not actually be available at runtime. If this occurs, the plan will run with fewer workers than expected, which may be inefficient. I mean, this is underwhelming to that what we experienced. This could really just turn down your database. And actually there was also nothing for a change in the query planner or for the max parallel workers per gather parameter in the release notes for Postgres 15. So this, we would say this was a really rare problem we had there to solve. Yeah, and that's it from us. Thank you for your attention. Also for attending this talk. You could leave feedback for us using this QR code. And if you're now also a Cloud Foundry fan, we have also some stickers. You can just ask us, or we leave it there at the sticker desk. And with that,
thank you for the great talk. And right now, let's go to the questions. Just raise your hand and we can come to you.
Hello. That issue is the failed migration you were just showing. Do you know why it was only an issue on one environment?
no. Yeah, it surprised us also. But this database and the foundation had a different workload pattern than everything else. So, and yeah, what was really nice to hear yesterday that also Postgres 18 you can dump the statistics and play them into your test systems. This might have this could helped us there, but we observed it only on one database.
Okay, thank you.
You mentioned that the random page cost is very different on various hyperscaler services.
Yeah.
Did you find that that actually reflects the sort of latency of the underlying disk drives, or are they like basically comparable? They've just chosen different defaults.
Yeah, they are comparable. There are differences. So you have, when you PG bench them, you see some differences, but they are not so different. So you get nearly the same, but when you have these high load scenarios, they may come into play. But these are some examples which we just observed. But also the random page cost was no issue in operations so far. So.
Anyone else? Oh, yeah, sorry.
Thank you. I was wondering if you could elaborate on the problems you had with parallelization. You were going from 11 to 15. I'm not 100% sure about Cloud Foundry. Foundry. Is this just for one foundry, or is it something universal you found?
This was only one installation, only one landscape, and only one database in this landscape. So actually, from our whole set of our database, it was only one.
Okay, cool.
So this was due to maybe the load and amount of data, and which were different in this particular database compared to the others.
Okay, thank you. I guess you don't have any idea whether the problematic behavior was somewhere between 11 and 15, but you don't know whether it was 13, 14, or 15?
No, we don't know.
Okay, sure. Thank you.
Okay. You mentioned that
Yeah.
you mentioned that you are offering, you are supporting any Postgres version between 13 and 16. Plans for update to 17, 18, which introduce better performance for vacuum and I/O and stuff.
Yes, I think, Philipp, this is for you.
Yeah, so the Postgres version 17 update is actually on its way, I would say. So there are already pipelines using this version, and yeah, does not take long. I would say that we switched the main pipeline of the CF deployment release to version 17, and once this is then tested there officially, we will also internally update to the newest version.
And if I may follow-up question. So I'm not sure if I fully understood, I never used Cloud Foundry. So basically, now you are talking about database which is supporting infrastructure. So basically database which keeps all the information about other services. But you also mentioned that you are offering database as a service for applications to use. So must those two be the same versions, or can I, for example, be supporting database 15 and then use, for example, database as a service as 16 or something?
Yes, it's like you asked. These are completely separated. Yeah, there's something which is called Open Service Broker API, and you just register endpoints from other service providers to Cloud Foundry, and then Cloud Foundry will communicate with them and provisions them. So you need just this implementation of this endpoint, which then causes the provisioning, and you can then do anything. They are completely separated.
Okay, thanks.
Hello. So I think you mentioned different options from different hyperscalers. So when you use it for the metadata, the brain of the Cloud Foundry for the infrastructure, did you observe any significant differences from throughput to performance and so on, or was it really similar for a test bed?
It is pretty similar, but it also depends on the load we have on different landscapes. So yeah, we have some landscapes which are pretty which have high usage, and there we have kind of other requirements than for landscapes which are yeah, in a really niche region where you have just a handful customers using the platform. So it's really hard to compare because there's nothing really which has the same the same load patterns.
Maybe a quick follow-up. So is it then you decide like on which hyperscaler and on which region to use, like based on the customer requests, like where they want their app to be deployed, or?
I would say we get these requirements from the product managers, and then we do it. It also depends on company strategy. So, yeah.
Thank you.
Okay, anyone else? Then thank you very much. It was really great talk. Please applause. Thank you.